Hello, everyone, and welcome to today's session on accelerating machine learning with a feature store. Thank you for taking time out and being here today. I would like to introduce today's speaker, Kevin Stumpf, who is here to talk on why and how of feature store and its importance for creating reproducible and repeatable ML applications. Kevin is co-founder and CTO of Tecton, where he leads a world-class engineering team that is building a next-generation feature store for operational machine learning. Kevin and his co-founders have built deep expertise in operational ML platforms while at Uber, where they created the Michelangelo platform, which in turn enabled Uber to operationalize thousands of ML applications in just few years. Prior to Uber, Kevin founded Dispatcher with the vision to build Uber for long-haul trucking. Kevin holds an MBA from Stanford University and a bachelor's degree in computer and management sciences from University of Hagen. Outside of work, Kevin is a passionate long-distance endurance athlete. Please join me in welcoming our speaker, and over to you, Kevin. Kevin, go ahead. Yeah.
Awesome. Thank you very much. As just mentioned, my name is Kevin Stumpf. Excited to be here, co-founder and CTO of Tecton, and we're an enterprise feature store that really helps you get operational ML into production. And over the next 30 to 40 minutes, I'll share a little bit about what is operational ML in the first place. What did we do beforehand at Uber, where we built an internal machine learning platform. Then I'll go into the technical problems that a feature store solves and shed a little bit of light of the things that you have to be aware of as you try to solve data problems for machine learning. And then at the very end, we'll show you how do you actually use a machine learning how to use a feature store as part of your machine learning lifecycle. So let's dive in and first look at what does operational machine learning actually mean. And the best way to show that is to contrast it to analytical machine learning. Analytical machine learning typically means that you have a human who's making decisions. You've got a human in the loop who's looking at dashboards or who's looking at reports like sales forecasts or churn predictions to send out marketing emails or something like that. Typically, analytical machine learning is run in batch, say daily, nightly, weekly, across data of your data warehouse or your data lake. Now let's contrast this to operational machine learning in the operational system. Here, you typically have machine learning applications that are directly driving customer experiences. And here, the machine learning application makes automated decisions at really, really high scale and really low latency because it directly affects your customer experience. So you need mission critical SLAs to make sure that the system doesn't go down and has great uptime. Common applications here are things like fraud detection or real-time pricing, product recommendations, or really anything around hyper personalizing your customer experience. And typically these operational ML applications, they're not just reading data from your data warehouse and your data lake, but they're also able to incorporate streaming data and real-time data. And before starting Tecton, I was at Uber and I was a tech lead and engineering manager of Michelangelo, the ML platform. And we started building Michelangelo in 2015 over there because back then there were a lot of data scientists who were trying to take advantage of this wealth of data that we had and use it for ML purposes in production. But it would typically take like anywhere from a handful of months to a year to get a new ML model trained and all the way into production because a lot of people were involved. Nothing was standardized. People were using bespoke frameworks. And it was overall just a huge hassle to get anything in production. And the key with machine learning to be successful, very similar to software engineering, is that you want to tighten the feedback loop from having an idea to implementing something to get it into production as far as you possibly can. Ideally, you just want to do it within a handful of hours or a handful of days and just rapidly iterate, rapidly experiment, just throw things out there into production to get feedback as quickly as possible to improve what you're working on. And with that mandate, we built Michelangelo, that centralized ML platform that all the data scientists, data engineers, ML engineers, software engineers are able to use to go all the way from having an ML idea to training the model, to evaluating it, to putting it into production and then serving it in production at really high scale within just a handful of hours. And this platform led to this Cambrian explosion of machine learning at Uber, and now it's powering tens of thousands of models and powers a ton of very diverse different use cases. Anything from customer support, ticket routing, to fraud detection, of course, recommendations, dynamic pricing, and a variety of other things. And as we built Michelangelo and looked at how did it have such an impact, and what are the problems that other companies typically face when they are trying to operationalize machine learning, we looked at what is an ML application even consisting of. And there we realized that an ML application is really consisting of three main artifacts. One thing is the application that wants to make a prediction. The next artifact is your ML model that is able to make the prediction. And then the third thing is the data that you need to use in order to make a prediction. And let me just come up with or showcase this with a concrete example. Let's say your application is an Uber Eats application, which is making restaurant recommendations. Now, this mobile app talks, of course, to a backend, which is making these predictions. This microservice behind the scenes with the API that the mobile app talks to, that is now your ML application that wants to make a prediction. Underneath it is the ML model that is trained, that is able to make these restaurant recommendation predictions. And then the third piece is the features or the data that is being fed into the ML model to make a prediction. And that could be a feature such as, what is the restaurant a user has most recently clicked on? Or what is the cuisine that a user has most frequently ordered over the last 7 days? And that brings up an important point here as well, to differentiate features from data. Like typically the way we think about it is that in this Uber Eats recommendation example, you would have raw data, which could be a transaction log of all the orders a customer has ever placed with Uber Eats. And another one could be a log of click events in the application, which restaurant has a user looked at. And so these are the raw data signals, and you want to turn those into high information density signals that your ML model is able to pick a signal up from to then make a prediction. And so now, as we look at these three different artifacts, of course, all of these three artifacts need to be developed and productionized in tandem with each other. You cannot just build the application and update your and ignore the model, or you cannot just update the model and ignore the data or the features. So it all needs to happen in tandem. And today we're pretty good at developing new microservices and APIs and putting them into production using common DevOps pipelines like Jenkins or Circle CI. We're also pretty good nowadays to train new models using your favorite TensorFlow, scikit-learn, PyTorch, what have you. Maybe you then wrap it up in an MLflow model container, and then you deploy it to production using an mlops pipeline. What we haven't really figured out yet so far is how do you efficiently develop new features and get them into production, serve them in production, and serve them consistently to training systems too. Typically, what a lot of companies are doing, and what we were doing at Uber early on too, was you would have data scientists work in, say, Jupyter notebooks or some other interactive environment, maybe even just on their laptop, work with a raw data dump, like this clickstream dump or the transaction log dump, and then do some Python-based data wrangling to aggregate this information into these higher order signals, like the most frequently ordered cuisine of a user, for instance. Then they train this model in their Jupyter notebook. They have something that they're happy with. It looks like it could actually predict preferences quite well. But if you want to now get this model into production, you now have to not just get this model into production, but you also have to get the features into production. And the feature code right now just lives as this Python code in your Jupyter notebook, able to transform data from CSV files that you've gotten from some data dump. Of course, that's not going to cut it in production. And so what happens is that the data scientist typically has to work with an ML engineer or a data engineer to re-implement the feature extraction logic using production-ready code, like in, say, Java or you would build Spark pipelines or Flink pipelines or something like that are able to process the raw data, turn it into features, and then serve these features from a key value store, say, in production. All of that takes a very long time and kind of impedes a data scientist's ability to move really fast. And so the solution to that, you may have guessed it, is the feature store. And the feature store is really what we call the interface between the data, the raw data, and the models. So it sits on top of your raw data sources, your streaming data sources like Kinesis or Kafka. It sits and connects to your data warehouse like Snowflake or Redshift, and to your data lake like Delta Lake or just pure S3. Then it's able to transform that raw data into features and serve them at low latency and high scale to your model running in production. And as well, it's also able to serve these historical feature values to your model training pipelines using a more like large scale batch interface. So you've got these two different interfaces to fetch feature values for two very, very different query patterns. Model serving only cares about the most recent feature values at really high scale and low latency. Model training cares about what did the world look like over the last couple of years. It doesn't need to be super low latency, but it needs to be really high scale. It needs to be able to process tons and tons of data. The data scientist will be the primary person interacting with this feature store, defining new features, deploying them to production, and then sharing them with other teams. So let's look at the technical problems that a feature store is actually solving under the hood. Why do you need it in the first place? And what's actually so hard about serving raw data or transform data in production? One big challenge comes from the fact that features are extracted from a variety of different data sources, like the batch sources and streaming sources and even real-time sources. And you need to turn this raw data into feature values that the ML model can make a prediction on. And that serves a ton of different challenges that I'll go through over the next couple of slides. One is different data sources typically have very different characteristics about the data that they store, how much data do they store, the data freshness, and the types of transformations that you can run against them. So let's dig into this a little bit and look at, say, a data warehouse, a stream, and a prediction request data. And prediction request data, by the way, is data that you have available right at the moment of making the prediction. So in the case of making restaurant recommendations with Uber Eats, it would be the GPS location of the user as the user is opening up the mobile application. So right there where you make this prediction, the GPS location is known, but it's not known on a stream, and it definitely wasn't known a day ago in your data warehouse. Now looking at these different data source types, of course, your data warehouse or data lake would have typically the complete history, the complete context on a user and all the transactions. But your stream typically only contains data of, say, the last 7 or 14 days in the case of Kinesis. Data freshness is very different too. Of course, your prediction request data is as fresh as it possibly gets. The stream is in the order of milliseconds to seconds. And your data warehouse may just get its data landed every couple of hours or every couple of days, depending on your data engineering infrastructure. Now, that already is not, if that weren't hard enough already to wrap your head around as a data scientist, the transformations that you can run across these data sources is also very different. Your data warehouse, you can, of course, run really large-scale batch predictions or batch aggregations and joins across any data that you've ever collected, but you can't do that on a stream. Small-scale batch predictions or aggregations you can run against transactional stores. Time window aggregations, you can now finally also run on your streams using systems like KSQLDB or Flink or Spark structured streaming. And then row-level transformations, you can also run against the prediction request data. But you see there are a lot of these cells here where you're not able to run certain types of transformations against certain types of data sources. That can become quite confusing and challenging as you try to develop new features and be innovative about it. Now, the next sub-problem here is, how do you even calculate the feature and give it to your model running in production, which has really stringent latency requirements? Imagine again the Uber Eats example where you want to run a query that says, what's over the lifetime of a customer the most frequently chosen cuisine or restaurant? Of course, your microservice that's making the prediction using the model cannot just talk to your data warehouse and run a lifetime aggregation on demand. That would take minutes or hours to complete, and you could never make a prediction in time to satisfy the user. So what you have to do is typically add some sort of a cache and decouple the feature calculation from the feature consumption. So you'd have an ETL pipeline somewhere that runs on a schedule and that pre-calculates these feature values and then stores them in your production store. And then your model would be fetching the feature values not from the raw data source anymore, but from the production store. And that decoupling now allows you to drastically, of course, reduce the latency to fetch a feature value in production. But it comes with a challenge. Besides, of course, wiring all this infrastructure up, you also have to find the optimal freshness and cost efficiency trade-off. Because you can imagine that the fresher you want a feature to be, the more frequently you want it to be updated, the more expensive it's going to be because you run the pipeline more frequently. And it really depends on the feature and the use case, what the optimal trade-off here is, what's the benefit and the lift that you get off by a fresher feature with the model in production, and what's the business impact? Does that justify the cost increase in a more frequently run ETL pipeline, or does not? And there are also even big differences, like for instance, a 2-week aggregation, like a 2-week click count aggregation, you typically do not need to update every 1 second or every 1 minute. It's oftentimes quite fine to just update it every 1 hour. While if you have a 30-minute aggregation feature, you do want to update it every minute or even more frequently than that, because the variance is just very different of these longer versus shorter time windows of features. And of course, all of that gets really messy if you're combining raw data from various different data sources, from your stream like Kafka or Kinesis, from your data warehouse, and potentially even from your prediction request data, like this GPS location that's being funneled into your application and then makes it to the prediction service. Now just imagine having to build a system like this that handles all these raw different data sources, combines them properly, then pre-computes features properly, choosing the optimal trade-offs. All of this can be done, but it's very, very hard. Another common trap that people run into who try to solve these data platforms for ML manually is what's called training serving skew. And that happens when the feature calculations that you use for production serving differ ever so slightly from the calculations that you use to produce the feature values for the training purposes. So imagine there is a feature which is what's the most recently ordered cuisine of a given Uber Eats user. Now, there are new customers too who've never ordered something. And so what are you going to do with that type of feature? Would you, for a new customer, say that cuisine is null? Or would you just use the most frequently ordered cuisine of any other user on the platform? Both could work, but what's important is that you're consistent between what you're doing in training and what you're doing in serving. Because if you deviate ever so slightly between the two, you've got the problem that your ML model is now trained on data that it will never see as such in production. And the result of that is that you may be training a model and you may be back testing it offline and you may see phenomenal results. But as soon as you throw the model into production and try to actually use it, the model performance completely tanks, and you've got no idea why that is. And oftentimes a common reason for that is these different introductions of training and serving skew. So the right and safe way to do this is that you just have a common implementation for the calculation of the features in training as well as in serving, because then you cannot introduce these discrepancies between the two. Another common source of train serving skew is introduced by timing discrepancies. And let's pick another Uber Eats example where you want to predict how long is it going to take until an order is going to be completed by a restaurant. A good feature to make such a prediction is the trailing 30-minute order count of a restaurant, because that's a proxy for the busyness of the restaurant at a given point in time. And in this chart here, you see two different humps. One is over the busy lunch hours, and the other one is over the busy evening hours. And you see that, of course, these values change ever so slightly every couple seconds, really. However, when you want to use this feature in production, what you would oftentimes do per this decoupling of feature calculation and feature consumption, you may recognize that it's totally fine to just update this feature value every 5 minutes, whatever the right cadence is. And so the distribution you would be observing in production looks more like this, with like a step function type graph, which is not as smooth as the true value distribution. And that is totally fine as long as you don't make the mistake of using a different type of granularity for training. Because what a lot of people would do is they would now actually train their model against feature data that is calculating the exactly accurate trailing 30-minute order count as of any given point of time in the past. Because you can do this when you run a large-scale batch process that may not actually that hard or that expensive to do, so you can do it. And so you may think, okay, great, it'll be a fresher feature value. This will probably give me a better model. But the problem is that, again, your model is now not given the chance to get used to the noise that it would actually be observing in production. And so the model is likely going to perform worse in production than it would if you had trained your model on feature values that follow this very same, much less granular distribution that you're also serving to the model in production. And then finally, another common source of train serve skew is what's often referred to as data leakage. Data leakage means that you're including information in your training data set that you would have never known of in the production system when you make a prediction. Let me make this more concrete. Let's assume you want to predict how long it's going to take to travel from San Francisco to Palo Alto. And you have a bunch of historical trips with their start time, their end time, and how long it took. And you may think, hey, one great feature to predict how long it's going to take is whether there was an accident on the highway. And you add this feature, and it's a Boolean, was there an accident or was there no accident? And if you now train this model against this historical data set, you may have a pretty accurate model, because if there's an accident, it's probably going to predictably take longer to travel all the way down to Palo Alto. However, you're probably picking up on this already. Later on, when the model is in production, it wouldn't know whether in the future, after you started a trip, whether there was going to whether a traffic was going to happen. It cannot look into the future. It can only look at what's happening right now and what has happened at any given point of time in the past. And so when you train a model, it's extremely important to not introduce this data leakage and only focus such a feature on, say, the historical distribution of accidents on this route from San Francisco to Palo Alto. And you may have guessed it, a feature store can solve all of these problems that I've just mentioned. It sits and connects to your batch data sources, to your streaming data sources, and to your real-time data sources. It transforms those raw data sets and turns it into features. And then it serves the features to your training systems without introducing data leakage. And it serves the exactly equally calculated feature values to your model running in production, really preventing you from any introductions of train serving skew. And all of that, of course, leads to higher quality predictions, and it leads you to deploying features and models much more quickly into production. And then it goes back to what I mentioned at the very beginning. It just condenses down this iteration and this feedback loop of training an ML model and getting it into production. Problem number two. ML teams are stuck building complex data pipelines. And I explained basically with problem one already why you need these data pipelines, why they're so complex, what are all the things that you have to be aware of. Now, without a feature store that does this automatically, data scientists need to partner up with data engineers, ML engineers, as we had to do it in the very early days at Uber as well. And as you can imagine, a data engineer has a ton of different priorities, getting pulled into a ton of different directions as well. And they'll have to put in their backlog, they'll have to prioritize it, then implement it. It'll take a long time, and it'll expand now this iteration loop of training that ML model and getting feedback from the production system for the data scientist. The feature store solves this problem because the data scientist is now empowered to really self-serve deploy features to production. You add a new feature to the feature store and you hit a button, the feature is pretty much immediately available for serving in production. Another problem, of course, without a feature store is that if data engineers have to implement these one-off data pipelines, that typically leads to no standardization. So it's much harder to maintain. Of course, it depends on the company and their best practices and whatnot, but it's harder to standardize. And oftentimes it can also lead to a lot of duplication of these data pipelines where different data engineers may not know of the work that the other person has done. So they may reinvent the wheel, and now you have all these different very expensive data pipelines running in production that unnecessarily compute the exact same feature values. All of this can be avoided with a feature store because it manages these features really as central data assets that can be browsed, that can be discovered, and that can be shared between different teams and between different models. Finally, problem number 4 is that typically when you have an ML model running in production and it breaks, it's not that the ML model itself breaks. It's that typically, because we're pretty good now at running an API endpoint and monitoring it and restarting it if it crashes and whatnot. But what does break ML systems in production is typically data issues. And there is a whole slew of these data issues that you have to be aware of. A very obvious one is that an upstream data source, like the click stream to your Uber Eats backend, may just be completely broken. No new events are coming in anymore because maybe your Kafka broker went down or something else happened. Or there may actually be a feature drift happening because the world is changing. And so the way you would detect that is you would want to look at the feature statistics of your features of the training data set that you used to train your model. What did the mean of your features look like? What did the standard deviations look like? What did the different categories of categorical features look like when I trained my model at some point in the past? And then in production, you want to keep an eye on those feature statistics and on the categories of your categorical features and notice when things start to drift away from what the model was trained on in the past. Because if you don't do this, your features are drifting. And again, that's basically another source of train serve skew, if you will. And we've talked to some companies where it's so hard to train a new model and get into production that they just trained a model literally 2 years ago, and it's been running in production ever since, even though the world around it has been changing. And depending on the use case, sometimes you have to retrain a model literally every hour, every day, every week. It completely depends on the use case, but it's rather uncommon that you can just leave a model completely untouched for years at a time. What can also easily happen is that you have opaque feature subpopulation outages. Now, that's a mouthful, but what does it actually mean? Let's again go back to the Uber Eats restaurant recommendation example. You may look globally at the performance of your model and how accurate the predictions are, and things may look really good. But if you just look at the global prediction accuracy, you may completely miss that the predictions in Germany or France have gone off the deep end. And it's just so few predictions that it doesn't tear down the global predictors. But you may still have these subpopulation outages happening and affecting just France and Germany. And even worse, even there, for these two countries, the predictions themselves may still be fine enough. They're not completely broken, so you don't really notice it, because maybe half of the features or all of the features but one are still working just fine. But one feature is completely broken for the subpopulation, and you're not going to notice it until you dig really, really deep. And then finally, even if you're aware of data quality issues and you know that something's broken, it's oftentimes not clear who should even own it, who's responsible for a certain feature, and who's got to track down what's broken and get it fixed. Now, a lot of these problems can be solved with a feature store as well, which, given that it runs feature transformations for you and that it serves feature values for training and serving, it is uniquely well positioned to monitor the quality of your features and look for data drifts, because it is aware of what did the features look like when you generated a training data set, and what do these features look like now that I'm serving in production. Do I need to tell the data scientist that there is likely a drift happening and a model should be retrained? Great, let's tie it all together now and look at the components of a feature store a little bit more deeply. As I already mentioned a few times, feature store ingests data from streaming and batch data sources and serves the feature values to model serving systems or to model training systems. And the core components of a feature store contain a registry, which is a catalog, and a web UI where you can browse features. Of course, you can also plug it into existing data catalog systems if you already have some. It has a serving system, an API that's running in production that is able to serve these feature values to you at low latency and high scale. It is able to monitor the quality of your features and then alert you if things go wrong. It's also, at least Tecton in our case, is able to also pass on these monitoring signals to your existing monitoring solutions, say Datadog or Prometheus. And then we've got the transformations and storage components. And transformations runs the feature transformations against the stream or against the batch source. And the storage component stores the feature values for both low latency serving in production and for large scale serving of historical data for training purposes. Now, one thing that's important to call out here is with this transformations and storage systems, Tecton does not come with a built-in transformation system, which is implemented from the ground up, or with its own database where it stores feature values. Instead, Tecton as a feature store really plugs into your existing data platform. And if your existing data platform, say, runs on AWS and you use EMR, then Tecton would plug into EMR to run Spark jobs there or to run Flink jobs there. So it doesn't just come up with its own transformation processing engine or something like that. It just plugs into the best of breed, different types of feature and really compute and data processing systems out there that already exist in your data platform. Similarly, for the data storage, we may be storing the historical feature values in your existing Snowflake or Redshift cluster on your existing S3 bucket. We don't come with our own proprietary data storage system. And then for the online serving, we'll be storing things in feature values in, say, your Dynamo cluster or in a Redis cluster, for instance, that's part of the existing data platform. Let's now take a quick look at how do you actually use Tecton as part of the ML lifecycle. And David, who's part of my team, is going to show you a demo in a little bit. But I just want to give you a quick, very high-level overview. You define features as code, typically in a file system, in a bunch of Python files, which you can bag in a Git repository. You can define these feature transformations using SQL, PySpark, or just Python code. You annotate them with a bunch of metadata where you'd specify, for instance, do you want to serve it online? Do you want to serve it offline or not? What entity is it attached to? Then when you generate training data, you would use the Tecton Python SDK in your Jupyter notebook or your Databricks notebook or your EMR notebook, whichever one you use, to fetch historical feature values to then generate your training data set and fit your model against it. And then if you want to serve feature values and fetch them, you would fetch them either from our REST or gRPC API, or you can, of course, use our Python library as well to just fetch a feature vector here. at very, very low latency, and then make a prediction using that feature vector. So how does the feature store help your team bring it all together? It allows you to build more accurate models while leveraging all of your data and ensuring this key data consistency between training and serving to avoid train-serving skew. It allows you to really tighten down this feedback loop for the data scientists to get models into production in hours instead of weeks. And finally, it brings DevOps-like best practices to feature development, which is really, really important to us, where we manage features as code in a Git-backed repository, so you can integrate it with your existing CI/CD pipeline, you can integrate it with your existing pull, request, review processes, anything that you use for your software engineering stack, you should also be able to use for your machine learning operational machine learning stack. Of course, we allow you to reuse and share features, monitor the data quality, and very, very importantly to us is, of course, security. How do you control data access? How do you make sure that only the right data scientists have access to the right sensitive type of data? And for what purposes are they allowed to use the data? How do you ensure that different teams are able to work in their isolated environments and not by accident bleed sensitive data between teams? All of that is extremely important to us. And that's what we've invested heavily into as well. A quick case study on how Atlassian has benefited from this. We went into production with them over a year ago now, and were able to reduce their time to deploy models from months to literally days. It now requires 0 engineering time to define and productionize features. There's now perfect offline-online parity, and as a result of all of that, not only are they able to train new models faster and get them to production quicker, but the model accuracy has also gone up by up to 20%. Now, if you think that a feature store is right for you and you're struggling with operational machine learning, there are 2 ways for you to get started. If you prefer a completely free offering that's fully self-managed and open source, you should take a look at Feast, which is an open source feature store that was originally created by GoCheck, that we're now heavily contributing to. It allows you to ingest pre-computed feature data from upstream pipelines and serve them in production as well as your training pipelines. If instead you prefer a fully managed cloud service that you don't have to manage yourself, that comes with SLAs and that supports batch streaming in real-time data sources, and that is also able to run feature transformations using Spark or Flink or Python, then you should take a look at Tecton and ask for a free trial. Awesome. And with that, I will hand it over to David Hershey, who's our first solutions architect at Tecton. He's going to walk you through a demo of Tecton now.
Thank you, Kevin. Super stoked to share a demo and hopefully put everything you've seen into some more concrete context. So let me start sharing and we can get going. Great. So what I want to walk through for this demo is just a really high-level data science workflow. In particular, what we're going to do is take some model that we already have in production with features being served by Tecton to that model in production. And we're going to build a new feature to try to improve or enhance that model. And we're going to see what it looks like to build a new feature in Tecton, how we can then use that new feature and all of the other data that we've used before to train a new version of that model. And then we're going to see what it looks like to integrate that new feature set into production and start serving features to our production model in real time. And before I dive into that whole use case, I just want to spend a second looking at our user interface and just giving you a sense of what you can discover when you boot up the UI and start modeling with something like Tecton. And so first thing you see is a view of all of the features you already have defined. This can be your team, you've defined, your enterprise. This is all filterable and searchable, so you can discover features made by someone or about some entity or by some team. And if you click into any given feature, you get a real snapshot of all of the metadata associated with that feature. So who made it and when and things like that. You can see exactly what actual transformations are being run to transform raw data into these feature values. And we'll talk about where these are defined in a second. You can see information about the actual movement of the underlying data. So in this case, Tecton is managing and orchestrating pipelines that are running, and in this case, Spark jobs that are actually transforming data proactively and landing into the feature store. And so we can see information like how fresh that data is, what the status of the various jobs that are actually proactively running that data are, and information about the actual lineage and flow of this data, like where the data is coming from, what transformations are being run, and how that's being stored. And finally, we can get a glance of summary statistics of the actual features so we can more quickly diagnose what this data actually looks like and get a sense of what you're actually using for your models. And so what this UI becomes is a primary tool for you to discover features that already exist and to reuse them when you go to model. So either discovering some new feature that you didn't know about that you think could enhance a model that you're working on, or just having a place to keep track of all of the stuff that you've already built so you can more easily reuse it. This is a really effective tool for that. So getting back to that use case, the model that we're going to work on that most of these features you see are describing is a model that's predicting if some user, when shown some advertisement on some website, what the probability is that they'll click on that ad. And what we have in Tecton to actually service models, so which is to group all of the features you want for a specific model, and then to provide those features either for training data or to the production model, is something called a feature service. And so in this case, we have the CTR prediction service that has grouped together all the features we're using for the model we currently have and is currently being used to serve features to that model. And so we can look at the exact list of features that are currently being used for that. And what we see is it's a whole bunch of things like historical ad performance, how many times ads have been clicked on, user behavior, so what users have seen, what they've clicked on, that kind of thing. And so our goal for the rest of this demo is going to be to build a new feature, to add it to this service. We're actually going to create a new version of this feature service, then to use that feature service that we create to actually generate new training data and to serve a new model. And so I'm going to flip over to an experimental workspace. In this case, it's a Databricks notebook where I'm going to start interacting with the raw data and do the basic exploration I need to do to start defining a new feature. So the first thing I'll do is reach out to Tecton and actually grab some raw data that I've registered with Tecton. So in this case, this is a Hive table that Tecton is connected to that has information about users, like their when they signed up, their names, their date of birth. And the feature that I'm going to try to add to our model is the age of a user when they see some advertisement. And so to start working on the transformation that I need to use to actually build that, I'm going to grab just a snippet of data from this data source, like 10 rows of it. And then I'm going to write a simple Spark SQL query to transform from date of birth to their age in years in this case. And so I can actually execute this query against that data and validate, that this feature actually looks reasonable. And at this point, I have more or less in the abstract sense defined a feature. The feature is a user's age at some point in time. It's associated with some join key called user ID, and it's being generated by this transformation that I just wrote. And so what's left to do is to actually take this transformation that I just defined and describe it to Tecton such that Tecton can start executing this transformation and storing the values of this feature in the feature store so I can consume them for modeling. And so as Kevin told you, features and everything in Tecton is defined in code in a repository. And so what I'm going to do is actually move over to that repository and define the feature there. So what you'll see is there's a whole bunch of files here that contain all of the other feature definitions that you already just saw in the UI. We're going to create a new file to start this user age feature. And the first thing I'll do is actually define a transformation. And so we're going to tell Tecton that this transformation that we just wrote should run against that Hive table that contains users' sign-up dates, names, and ages. And then we'll write that exact same query that we wrote in Databricks, except I'm slightly going to tweak it to programmatically inject a date instead of just using current date to calculate it. And so this is going to allow me to do some form of time travel and calculate historical values of features. Notably, as we said before, this is Spark SQL, but you can also just write PySpark. So in that case, you'll get a data frame as input. You can write whatever arbitrary PySpark you want and produce a data frame on the back end. And so you really have a lot of flexibility in terms of how you define features in Tecton, and it sort of allows for a wide range of what you can define. But in this case, we'll take this Spark SQL query we wrote. It's called this transformation. And the next step is going to actually be to create a feature out of this transformation. And that's what I'm going to do down here. So I have this user age and years transformation, which I'm going to use down here. I'll give this feature a name and a description and some other metadata. And then the last really interesting thing I'll do is tell Tecton what to actually do to materialize this data. And so in this case, I'm going to tell Tecton to build a feature pipeline that writes values of this feature into the online feature store for really fast serving, to the offline feature store so we can keep track of historical values of the feature. We're going to historically backfill data. So this is going to proactively calculate values of this feature for the last 6 months so that we can more quickly retrieve those values when we generate a training data set. We'll schedule new jobs to actually calculate and update values of this feature every 30 days. So this is one of those trade-offs that Kevin explained where this feature in particular is not particularly sensitive over time. So we don't need to be very proactive in calculating new values of this feature, and we can tune down how often we update it. And so with these two pieces, we have a transformation, and Tecton knows how to use that transformation to actually materialize data into the feature store. And so the last thing I'm going to do in code is update the feature service that we had before to include this new feature that we built. And so this is what that current feature service looks like. And it's using this group of features today. And those are the features we saw when we saw that feature service in the UI. I'm going to actually copy and paste this feature service and just make a few tweaks. The first is we're going to add that new feature that we created. That's the user's age. And the second is we're going to call this version 2, which will create a first class variant of this feature service. And we'll see what that actually looks like in the UI. And we can't forget to import that feature from the other file that we just defined. Now that we're here, the last step is to actually sync this repository up with the Tecton cluster itself. And so for that, we'll use the command line and use this call Tecton apply, which will comb through the repository, validate all of my definitions and make sure they're all sane and runnable. And then tell me everything that's going to change, confirm it with me. And as soon as we apply this, we can head back to the user interface and immediately see that our new feature has been created. Including Tecton has scheduled a bunch of Spark jobs to start calculating values of this feature. So we can actually start consuming these values to do things like generate training data or service our model. The other thing we created was this feature service variant. So this is what we had before. We've created this V2 variant that contains that new feature that we created. So this click-through CTR prediction service V2 is what we're going to use to generate training data. And to do that, I'm going to flip back over to an experimental workspace. And the first thing I'm going to do to actually generate training data is basically decide what training data I want to fetch. And so in this case, the model is predicting if some user, when shown some ad on some website, will click on that ad. And so we have a whole bunch of historical data registered with Tecton. That is a whole bunch of events in the past where users were shown ads at some point in time and whether or not they clicked on those ads. And so with this data frame that contains the join keys associated with all of our features, the timestamp of some event, and this is going to essentially be the labels for our data, we can reach out to that CTR prediction service V2 that we created and pass in that data frame that was right here. And what Tecton will go out and do is join on the values of all of the features in that feature service to this data frame and effectively generate our whole training data set. And so in practice, what that looks like is it's saying when this user was shown this ad on this website at this point in time, in the last 7 days, that ad had been clicked on 33 times. In the last hour, that user had seen 2 advertisements. And our new feature over here, the user's age, we can see that user was 40 years old. And so when we do this, Tecton is handling a whole bunch of fairly complicated things. It's doing time travel and telling you what the values of these features were at this point in time. As Kevin very clearly explained earlier, it's not just calculating the exact values of these features at this point in time with the full knowledge of historical data. It's telling you what would have been stored online at this point in time. And so what that does is help to eliminate any possibility of training serving skew by producing data that looks exactly like what would have been served historically at that point in time. So now we have this data set. This is just a data frame. We can take this to Pandas or Spark, save it to some file, prepare it for TensorFlow or PyTorch, whatever we do, and basically train a model with whatever tools you currently use to train a model. And then you can deploy your model with whatever tools you use to deploy your model, whether you're hosting your model as an endpoint or embedding a model directly into some application somewhere. And the real payoff of using Tecton to train your model like this is that at inference time, you have an incredibly simple and convenient way to get the data you need to your model when you go do inference. In practice, what that looks like for a model like this, you may have, say, a user browsing some website, and you want to decide which of 10 ads to show them. So you want to score all 10 ads against your model and pick which one will be the highest probability. And so you'll pass in an advertisement, the user ID, the website they're on. And what Tecton will do is go grab the freshest value of all of these features for that ad, user, website, and get them back to you in the exact format you need to actually pass into your model. I wouldn't be surprised if this fails right now, and that's anticipated because this data is still materializing. So we're doing this actually live to show what actually happens here. And you can see that these materialization jobs for the user age feature are in the process of running. Once these Spark jobs actually finish, this data will land in the feature store and data will be available to consume. This will stop erroring and we'll be able to actually start consuming data out of the feature store. And I expect that will happen sometime in the next roughly minute. But just to highlight, instead of having a complicated sourcing process where you have to reach out to all of various different production data sources or run different queries that you had to re-engineer, this is just a single REST endpoint that you're hitting associated with that same feature service you use to get your training data with a simple set of keys that you need to retrieve data. And with that, you can very, very simply build production applications. It very often looks like these exact 2 lines of code where you get data from one service, pass it into your model with another service, and you have your scoring right there. And so the complexity of building this production application has gone from something that takes months and months to a handful of lines of code that you can generally integrate in the same day. One other thing to note about how Tecton manages this is we also outfit monitoring on these prediction services. And so the feature services you create, Tecton outfits with monitoring that tracks latency and the uptime. And Tecton being a managed service, our engineers are around to make sure that these latencies and this uptime is always working for you. So frequently getting data to your models, and these models themselves will become really integral parts of the user experience of some application. And having a team like Tecton's team here to support making sure that those endpoints are responsive and that your models are functioning properly really make sure that your machine learning models are doing what you expect all the time. All right. In the interest of time, let's see if this has finished materializing one last time. It has. So the data is materialized, so we can see that I have the latency because I'm running to the West Coast. So this took 130 milliseconds to get to the West Coast and back. But we can retrieve features in real time, pass them into a model. It becomes really simple. And yeah, so we got 6 minutes left. I will hand back off so we can have a little bit of time for questions. Maybe Kevin can pop back on, or I'm happy to field anything. But I hope this was helpful illustrating what Tecton can do.
Thank you, David, and thank you, Kevin. It was really interesting because feature store is pretty key today to machine learning lifecycle, right? We cannot create ad hoc features when we need it, and features are shareable because if you take some domain like fraud detection or any other domain, there'll be multiple fraud use cases where you can go and tap onto a common set of features that multiple data scientists can use for their experimentation and hypothesis, right? So it was pretty good detailed information. There are a couple of questions that I have before I jump on to questions asked. So when we talk about model training, right, we typically have an batch-oriented system where we need to scale our model training process. And when we deploy the model, typically we need extremely low latency, maybe a milliseconds or something like that. So the storage part of it, how are you kind of managing the storage when we have to do lookup in real time? Basically, we get such low latency and not really relying on batch infrastructure.
I'll go for it. Yeah. So there are a lot of different little tricks, and then there's some high level stuff. So the high level stuff is keeping fresh values of features in some sort of low latency, frequently like a key value store that has really low latency lookup. And so what you typically see, like Feast is using Redis more often. Most frequently, we're using DynamoDB behind the scenes for this. Those things have different trade-offs. I think Dynamo is a really, like for most use cases, is a really good tool for this, but Redis also is. And the way that Tecton's heading, on a side note, is just to make it so that we use the right infrastructure for the right thing. One other thing behind the scenes is we just make sure we do some optimizations, especially for things like aggregations and how we store those, so that we can do really quick lookups of those, what are traditionally more complicated features, to get the right values of at inference time. And that's just, a bunch of optimizations we've learned through years of experience to make it so that pretty much the whole set of features is we're able to look up in real time.
When you talk about like Dynamo and everything, that these are like AWS specific services. If I go to Google Cloud, I have Bigtable, or if I go to Azure, I have a different key value store. So how much of this is more customizable depending on your end user need? So can it just like plug out DynamoDB and maybe plug in Bigtable? Is it that easy? How is it?
Yeah, so Tecton today runs on AWS, but Tecton is built in a basically cloud agnostic way. And we then build these adapters for cloud vendor specific infrastructure like DynamoDB or Redis, and currently Delta Lake and EMR on AWS. We're in the process of adding support for BigQuery as well. And so we will, over time, the next cloud will be GCP that we'll be supporting most likely, and then we'll be adding support for Azure as well. And so the platform is built cloud agnostic, and now it's just a matter of adding adapters to the data platform pieces of the other major cloud vendors that we want to support.
Got it. So let me take some questions from audience. So this is from Shakti. His question is, what if we train the model and new features need to be added after weeks in that model? So what step we need to follow to add those features and retrain the model?
Yeah, so you would typically create a new feature in Tecton, which is whichever one you want to add. And then you would, as David just showed, there's a feature service, which is typically you have a one-to-one mapping between a feature service and a model. So now you've got the old models that are running in production pointing at the legacy feature service, so to say. Now you create a V2 feature service, as David showed. You add this new feature in there, productionize it, and behind the scenes, all it's really doing is giving you a new endpoint in which it's joining in this additional new feature that you've just added. And then you go to your training environment. You now ask Tecton for the feature values from this new V2 feature service you've just created, create this new model, and then roll it out into production, where now the API or the service running in production uses your new V2 model and knows to now go back to Tecton and fetch the feature values for the V2 feature service. But both of those will still be running in production, the legacy feature service and the new V2 feature service. And then once you've changed your production system to the new model, you can deprecate the old feature service.
Got it. Got it. So there's one question from Maria. Is this service serverless auto scale? And this is a pretty interesting question because when we define our feature store, we may have hundreds of features, right? And you might have a time window by this needs to be completed, either 30 minutes or 60 minutes, whatever is scheduled. So how do you auto scale this entire engineering pipeline that goes into backend, that goes in the backend? Yeah.
Yeah, so we have this nice advantage that we are a cloud native feature store. And so as we run the feature transformations pipeline, we would spin up EMR clusters, ephemeral EMR clusters for the different features. So you add a new feature, that's great. It's not going to affect anything else. We're just going to spin up a separate ephemeral EMR cluster for that feature. Of course, you can limit the total number of EMR clusters you want the platform to maximally spin up. But that gives us basically infinite horizontal scale thanks to the cloud vendors. That's what we're doing on the materialization side. And then on the serving side, we're running our own, the API microservice, which is fully managed by us, runs on an EKS service, which is a Kubernetes cluster. And there we're able to look at certain health metrics, like what does the latency distribution look like? What's the memory utilization? And as we notice that the scale is getting to a point where we need to scale up the number of pods, we're then tapping into basically EKS auto scaling abilities to add new pods to the EKS cluster, and if necessary, even add new nodes to the EKS cluster.
Got it. Got it. There's one question: isn't it like auto ML? I think even auto ML requires like good features, and this is basically entry into an auto ML. You need good features for auto ML to do something good. Otherwise, it's just going to run across all the algorithms and give you some score, right? So I will skip this question a bit. May this is a pre-step to auto ML. So that's what I would say. And you can correct me if I'm wrong. Maybe I'm snatching your questions. Go ahead, Kevin and David.
Yeah, for sure. Redis and Dynamo, that's a very interesting question. And typically, Redis is a great store for you if the total number of features that you want to serve in production fits in memory for the Redis cluster. And then if you repeatedly fetch the same feature value over and over again for the same entity, like for the same user, then Redis is great because it's just serving it from memory, and you're not being charged by, say, AWS or whatever for every additional query. You have got the node, it's up and running, it's costing you a certain number of dollars per hour, and that's the cost. And that's great. However, with Dynamo, if you have a huge scale, a huge cardinality of feature values that just doesn't fit in memory anymore, for which you need to have such a distributed key value store, then you would want to use Dynamo. Of course, the cost of that looks very different, where with Dynamo, it's actually charging you per write and per read. And so even if you fetch the same feature value over and over again, it would incur costs that you wouldn't have to bear if you were using Redis. We do have a little trick here where we actually also support DAX for the listeners who are familiar, which is an accelerator on top of Dynamo, a cache on top. But it's still, depending on the use case, depending on the cardinality of your features and the distribution of requests for the same features of the same entities, Redis or Dynamo, one of them may be cheaper than the other. And so ideally, you do have a platform which allows you to pick and choose the ideal online store if you're tackling ML use cases at really, really high scale, where those costs start to matter a lot.
There's a question from Suraj. How can I implement this in Azure Cloud?
Today, you should use Feast for that. We've added support for Azure recently. In the future, Tecton will come as a managed service to Azure as well.
So going back to one of other question, right? Model monitoring, because that is key. Now you have defined your features, and as you are updating features, the features may drift over time. So I saw the Grafana dashboard over there, and it had a lot of metrics on the response time and everything, right? Do you also capture feature drift and alert? Do you have mechanism for that?
Wonderful question. David is answering it. So
yeah. So I'll touch on this in a few places because it is a really natural place that a feature store can fit in. So one project that we're working on right now is an integration natively with a tool called Great Expectations that will let you set quality expectations, set some rules, get alerted if your distributions change or if certain data quality metrics fall out of scale for features. And we'll make it really easy to get alerted on that kind of thing. And another thing that I'm working on right now, at the far end, there are some really incredible products out there for just monitoring models. So I'm working with the Fiddler folks right now, for example, on putting together a joint solution to show what it would look like to really take a best-in-breed feature store and best-class model monitoring. And the nice thing is those things fit together in a really, really quite simple way because we provide features. Those can go straight to Fiddler to monitor those. And so depending on what you're looking for, in our product, I expect we'll have a really awesome and flexible set of tools in the short term. And also there are great tools out there for monitoring that I think plug in really well with Tecton right now.
Got it. And I think that's it. We are also on the time. And Maria said, love that answer. Thanks. And even Shakti has said, thank you. Thank you, David. And thank you, Kevin. It was really interesting session. Good to know a lot of details about feature store that I did not know. In fact, I have built feature stores in the past. At that time, there was no name to it called feature store. We used to build for machine learning and accelerating it. But this was really insightful session on what are the key components that are required to make feature store, how you can share features, how you can collaborate between multiple data scientists and project. Thank you very much. Thank you for coming over here. And thank you for the excellent demo as well. Thank you everyone for joining. Thank you very much.
Thanks for having us on.